Thank you, Fred. And thank you to the organizers for hosting this wonderful conference. I've had a lot of fun so far. So for those who don't know me, yes, I work in Singapore with Alexia. And I'm going to take it away from the last few talks who really talked about energy and go to a more foundational thing, talking about entropy and a very broad perspective of inference. So I'd like to start by asking a thought-provoking question of what do you think of when you hear the word measurement? And based off of the field in the room, I'm going to assume that you assume a measurement as some sort of probe on a quantum system. And this probe gives you information about, depending on what you're doing, if you're doing a computation, it leads to an answer. If you're doing communication, maybe you're learning about the message. But I would say that this is a very narrow scope of what a measurement is. It's really the bread and butter of science and engineering alike. It's how we test models. It's how we make predictions. So in the last decade or so, there's been some huge breakthroughs, both testing models and predicting models with LIGO about a decade ago, and then more recently, Fermilab's G-2 experiment. But this doesn't have to be so grand. It can be, it's also everyday devices. So if you wear a smartwatch and you go for a run, and your watch is telling you where you are, how fast you're going, the direction you're heading, your cadence, heartbeat, so on and so forth. These are all measurements and based off of scientific models. And then just a little fun thing that I added at the end is that this idea of prediction and modeling has kind of superseded science into the social sciences. And so this Black-Scholes equation at the bottom is a very successful model used in the stock market for predicting price of options based off of Brownian motion. But I would say that number two, I'd like to label it as, instead, an application of statistical inference. And so that's the big part of, that's the second half of the title. So I want to make sure that everyone knows what this is. And from a very broad approach, you can break statistical inference into three base steps: some sort of preparation of a system, some sort of control and interaction, and then the measurement itself. So I'll work with a really simple example throughout the talk. So I just have some unknown coin that I want to measure. I'm going to let it interact with a meter, and then that meter will tell me what the coin is. So this is really simple, and I'll leave it as an exercise to the listener to scale this up to measuring the anomalous magnetic moment of the muon. But this is actually a little too simple because often you can't measure the system of interest or the observable of interest directly. Normally you have to repeat steps 1 to 3 many, many, many times. So for example, if you want to measure your position, more satellites, more measurements, better precision. Or if you're wanting to do some sort of image detection, more sensors, better resolution. So to incorporate that into the coin, we've introduced some sort of noise into our meter. I'm giving a very broad or a very vague description of how it works, but you can imagine that maybe my meter, if it's in the center, characterized by some property epsilon, that it gives me the incorrect result. So with half the time, if it reads heads, then with some probability 1 minus epsilon, it gives me the correct result, but with some low probability, I see the wrong thing. And so I'll have to do steps 1 to 3 many times to actually learn if it's heads or tails. And so how does statistical inference actually work? So as I said, I have to repeat and repeat, and then I have to construct what's called an estimator. And how you do this, it's generally broken down into 2 different branches, and I want to introduce these terms because we kind of steal their nomenclature in statistics and will eventually use it for measurement costs. So one school of thought is the frequentist school, and this stems from the idea that probabilities are just frequencies. And so one might say that I'm just going to label my estimate to be the most frequent outcome. So if I see a bunch of heads and only a few tails, I'm going to say that my estimate is heads. But I don't have to do something so concrete. And a very popular school of thought is also the Bayesian or the Bayesian strategy, which stems from Bayes' rule, and I'm going to update my estimator based off of the probability distribution. So I could have an estimate at the end that the coin is 99% heads and 1% tails. There's nothing wrong with that. And these are compared normally using some sort of cost function, like the mean squared error. And why we want to introduce this new framework is that this method is very ineffective at capturing the physical cost of the inference. So it doesn't really capture the preparation control measurements. So maybe some of you are very familiar with quantum metrology, where if I have a big entangling operation, I get this quadratic advantage with the same number of qubits. So it does capture the number of qubits, but it doesn't capture the fact that I've had to do this very expensive entangling operation. And so in the spirit of the QEI, and that there's real-world limitations, we should rephrase, this comparison to properly take into account the cost of doing our inference, whatever it is, whether it's measuring a coin or whether it's detecting a gravitational wave. And so we're specifically going to focus on the measurement aspect, as this is generally a very expensive part of, of quantum information. And we've already had two wonderful explanations preceding me, especially by Pierre Emmanuel, but I'll quickly go over again the MNR approach. So it's looking at the interconnection between the metric, so what we care about, either the cost function or something maybe more pertinent, if it's metrology, maybe Fisher information or verification correctness. Noise will be the measurement errors, and then the resource, which I've highlighted, is going to be cost of measurement, which I'll get into how we actually compute this later. And this is just a really flexible analysis because, as we saw, we can ask, given an allotted amount of resource, what is the maximum achievable metric, or given a target metric, what is the minimum amount of resources one can spend. Right, so we have the metric and noise. I'll quickly cover the measurement cost. So a measurement really has to be put into or partitioned into two different actions. One is going to be the actual measurement or the correlations between our system and the meter. And then there's a reset state that is your normal Landau erasure that you know it. And so the first part was really studied by Szilard a long time ago, and then Landau as well. But in 2010, or 2009, sorry, this was reconciled or re-looked at by Takahiro Sagawa and Masahiro Ueda, that said that you really have to look at both of these things as a collection, because if you make some assumptions, like asymmetric assumptions of the memory, you get some deviations. Whereas together, it kind of reconciles itself. So the derivation, it's actually not so complicated. They use the first law of thermodynamics, so work is just a combination of change in internal temperature or internal energy and heat dissipated. And you find terms that look like changes of free energy. H here is entropy of your measurement results. And what's left is this term, which they dubbed the quantum classical mutual information. And this was kind of highlighted in the measurement engine talk yesterday, as well as poster 17, where you're paying for correlations. So what they have, I won't delve too far into the math, but it's something that looks like mutual information, which is something of a quantity from statistics that is just quantifying the amount of information B contains about A, or A contains about B. So here it's the amount of information our meter contains about the system. But this derivation, it's very presumptuous on how the measurement works. I don't think it's bad per se. It's just some collection of projections. And unfortunately, though, it's very loose for inefficient measurements, which is what we're after. And so a nicer way to put it is, for the measurement cost, is a very general way. I'm not going to explain each individual term for the sake of time, but if I have some system, and I partition my apparatus into like the actual physical thing and then some sort of memory register. And then after the measurement step, I have some sort of outcome, but I'm not getting all of the information out of the apparatus per se. And this is due to the noise itself. So now my work cost for the measurement and the reset, it's some sort of like mutual information term again between the system and the outcomes. And then there's also residual correlations in the apparatus. This is due to the noise. And then if you ended up assuming that the measurements was just a collection of projections, you would recover the Salgo and weighted bound. Right, so this is just the cost of a single measurement. I originally said that in inference, you want to do this many, many, many times. And so what is the cost of several measurements? So we can either do this many spatial measurements at the same time, or we can do this temporally. I just have 1 meter, and each time I'm going to reset and do this again and again. And this is where I introduce frequentist and Bayesian for measurements. So the first cost, I can think of doing something very brute force. And I call this the frequentist approach, because I'm just going to do the same sort of measure and reset protocol each time. So I'm paying log 2 bits. So I'm going to get something that scales like n. Or I can do something Bayesian. I can adapt to the information I have thus far and take advantage of the fact that because my systems are correlated, my apparatuses will also be correlated. And I can use this information to update the measure and reset protocol to get something much cheaper in the long run. So the quick summary is that I have some sort of initial state. It's going to cost some amount of entropy to do the measure and reset. And then based off of my first measurement result, I can update the system of the state accordingly. And then the second time I measure the system, it's going to have a different cost. And I can repeat this as needed. And so the total expected cost is at the bottom, where I've averaged over all possible trajectories. So for the coin, the first cost I use base 2 logarithm is just 1 bit of entropy. And the second cost, regardless of the first measurement, is necessarily lower. It's characterized by the noise. So it would be like epsilon log epsilon plus 1 minus, or sorry, minus 1 minus epsilon, so on and so forth. And so in general, the measurement results are improving the quality of an estimate. It's updating our knowledge of the system. So these are very intertwined. And then because we have this updated and improved information, we can reduce the cost of subsequent measurements by taking advantage of these correlations. And there are some hidden assumptions here that I'm sweeping under the rug. So first is that you have the ability to tune the measure and reset protocol. And second is that thermodynamics is a law of expectations. And in inference, we have several measurements. So we're making the assumption that these averages hold true. So finishing up the coin example, if I have the frequentist approach, I'm going to get something that scales like n. And if I have the Bayesian approach, I actually pay some finite amount, regardless of the number of times I want to do a measurement. So now if entropy is the limited resource in question, I can basically get as precise as I want, whereas in the frequentist approach, I'm limited to some number of coin flips. So the first perspective that, okay, thank you. The first perspective that I want to look at is quantum metrology. I think those who know me from my PhD know that this is really my bread and butter. And the idea is just to infer some sort of phase using a qubit. So I start with a plus state. I'm going to encode some unknown phase into it. And I'm going to measure in the plus-minus basis. And I'll use those measurement results to determine theta. And just like the coin, I'm assuming my meter is a little broken. There's some probability that when it's plus, it should have read minus, and vice versa. So in metrology, the normal metric is the Fisher information, and this is something that scales linearly with the number of qubits if you're doing something separable, and there's some noise factor. And in this new framework, you again find that the frequentist method, it's something that scales like n, and in the Bayesian approach, we're getting a logarithmic advantage in the entropic cost of this experiment. So then if we had a limited number of resource, you would then get like a logarithmic extra precision in your estimate of theta itself, which you normally talk about getting an advantage from entanglement or squeezing, where here we're just saying, if you change how you do your measure and reset, we're going to get some sort of advantage. Right, so the next step is really also tuning the metrology protocol, but this is easier said than done, and I have not gone that far yet. But we do have a lot of, because this is an ongoing project, there's a lot of interesting perspectives here. The first one that kind of inspired this project is a multi-parameter quantum metrology problem, which is significantly more challenging than the single parameter one. So now I have maybe a parameter or a phase and an amplitude encoded at the same time. And in this realm, you can think of two different strategies. One is maybe preparing a bunch of states that are both kind of sensitive to the phase and the amplitude, and then another strategy where half of my states are really sensitive to the phase and half are really sensitive to the amplitude. In a metrology world, these are sometimes, like asymptotically, these are the same, sometimes. But I don't think from an entropic or an energetic perspective, I think one is going to favor the other heavily, or one will be much more favorable. Another one, an interesting perspective, so inference is really everywhere in quantum information, whether you know it or not, is verification and tomography, so more on the crypto and communication side. And be interesting to see just how many extra resources or how much extra entropy an adversary might cause. The third is looking at the duality of fluctuation theorems. So I would assume most of you know the fluctuation theorems for thermodynamics, but there is a parallel fluctuation theorems within statistics. And this would be much more applicable when you're not doing many, many measurements, something like error correction, where you just have, in the 3-qubit code, you just have two parity measurements. This in itself is inference, and seeing how these interplay, if at all. And the last one is any sort of time implications. I've been thinking about this recently, and I now think that it comes in as some additional noise. But if you're familiar with Landauer principle, you know that the standard assumption is that you have some sort of adiabatic expansion over an infinite amount of time, and I don't want to flip coins until the heat death of the universe. So how does time play a role in all of this? Or can we integrate it nicely? So a quick summary, as I think I'm kind of ending on time. This is a very fresh, I think, perspective on inference, and we're really just taking the assumption that these steps have some sort of cost, and we're focusing on measurement here. And the information that we get, it both improves our estimate of whatever we're doing, and it can reduce the cost of future measurements. And although this is from a very foundational point of view, unlike the previous talks that was more, I guess, tangible, this can be massaged into something bigger, including the control and the preparation. And as I just showed, there's a lot of nice applications in quantum information. So with that, merci beaucoup. And I guess stay tuned for hopefully the paper soon.
Questions? Oh, we have one.
Yeah, thank you for the very nice talk. I have maybe some basic questions. So when you discuss your basically setup, so you say you need to prepare, then you have this interaction and control, and then you do the actual measurement or readout. I'm wondering, are you also looking at the step where you need to reset everything and at the cost of resetting?
Yes, yeah, that is baked into, so this diagram might be a little oversimplified. There is a reset step at each time. We're not reusing the meter before resetting it. So we're really basing it off of this picture, and then we're just blowing it up many, many times.
And maybe another question, if you, like, in order to get a better estimate, you need to run this more and more. So the better, or the more you run this, the better is your estimate.
Yes, the better of the estimate, but then it's going to cost more.
Time. I mean, this goes to my next question. So time is also like a resource which you might consider.
It is, yeah.
Running time.
Yeah, I think putting time in both steps are very tricky, but a necessary thing. So I think time in the measurement step, it'll play a role in basically correlation. So somehow, maybe along the lines of like Wave theorem, Wigner-Araski, Sanas, and then the reset is more tricky. So if people have really good ideas, I'm happy to hear, but I agree that, yeah, you do have to take time into account. As this is often ignored also in just inference as a whole. Like in metrology, we don't really think about the time it takes to prepare and measure 1,000,000 qubits versus 1,000.